This video is on section 7.1 notes, law of sines. So first I want to talk about what it means when you're working with a problem and it tells you to solve a triangle. So when you solve a triangle, it means that you're going to calculate the length of the missing sides and you're going to calculate the measure of all the missing angles in the triangle. So that when you're done with the problem, every single angle has been labeled and every single side has been labeled. Next, we're going to define an oblique triangle, and an oblique triangle is just a triangle that does not have a 90-degree angle. So we talk about right triangles. This is the opposite of that. This drawing that I put up here is what you can use if you're drawing a triangle for any of the problems in this unit and you need to label the angles and label the sides. So we have angle alpha, beta, and gamma, which is kind of like ABC, but in Greek. So alpha, beta, and gamma. And then across from alpha, you have side A. Across from beta, you have side B. And across from gamma, you have side C. And one thing that we'll learn is that every time you're filling out the information in a triangle, you'll notice that the largest angle is always across from the longest side. The smallest angle, it's probably this one, the smallest angle is always across from the shortest side. So that's something to keep in mind. All right, now we're learning the law of sines today, but later we'll be learning about the law of cosines. And the law of sines and the law of cosines are used in different circumstances. So when you are given the information of a triangle, and they might give you a picture, but most likely they're just going to write out the information. They'll tell you the angles, they'll tell you the sides. When you have that information, if it's two angles and the side that's in between them, or two angles and the side that's not in between them, or two sides and a non-included angle, if it's any of these situations, then you're going to be using law of sines, which is what we're doing today. If it ends up being two sides and the angle that's between them, or if you're given all three sides of a triangle, then you're going to use law of cosines. If they ever give you a triangle that's not oblique, this would be oblique triangles. If they give you a triangle that's not oblique, meaning it's a triangle that has a right angle, then you're just going to do SOHCAHTOA, and you're going to use your regular trig ratios and think about opposite over hypotenuse or adjacent over hypotenuse or whatever, okay? So we're going to talk about law of sines, and when we do law of sines for oblique triangles that do not have a 90-degree angle, we're going to learn that the two situations that we're going to cover first, angle side angle and angle angle side, that those are pretty straightforward. They're pretty easy to do. And that the third situation, angle side side, is a little bit of a pain in the, you know what I'm saying. This is called the ambiguous case, and it's going to be the majority of what our notes are on today. Okay, so first two situations, we're going to solve an angle side angle triangle and an angle angle side triangle. So here they gave us some information. They said that angle beta is 34 degrees, angle gamma is 64 degrees, and side A is 5.3. So if I go through and I mark these, there's angle beta, here is angle gamma, and then here is side A. You can see that what I have just labeled is angle, side, angle. They kind of go in a row, angle, side, angle. So that's what I mean when I say an angle, side, angle triangle, is that the information they gave you is right in a row like that. And if that's the type of information you have, then you'll look and you'll say, okay, law of sines is the appropriate formula to use to solve the triangle. It's the appropriate formula to use to find the missing sides and the missing angles. So what I'm going to do first is just find this missing angle, because I know that three angles in a triangle always add up to 180 degrees. So 180 minus 34 degrees minus 64 degrees. And I'm going to be careful about putting my degree bubbles on everything. 82 degrees. So that missing angle, alpha, is 82 degrees. And I can go ahead and label it. There we go. Okay. And now I'm going to go ahead and set up the law of sines. So whenever I do law of sines, I always look at what pair I have. And when I say pair, I mean an angle that is across from a side where I have both pieces of information. So I'm going to say sine of 82 degrees over the side 5.3. And then I'm going to set that equal to another ratio, and it's going to be one piece of information that I do have and one piece of information that I'm trying to solve for. And so the information that I do have is the angle 64 degrees. What I'm trying to solve for is side C. The information that I do have is 34 degrees. What I'm trying to solve for is side B. So I'm actually going to have to do this problem twice. Equals sine 64 over C, and then I'm going to set this up again. Sine of 82 degrees over 5.3 equals sine of 34 degrees over B. All right, now anytime I'm solving an equation where I have a fraction equals a fraction, for me to solve that equation, I just need to cross multiply. So I'm going to multiply 5.3 times sine 64, and I'm going to multiply C times sine 82. And then to solve for C, or to isolate C, I can just take sine of 82 and divide it to the other side. So I end up getting that side C is approximately whatever this decimal is. Now, if you'll notice in this unit, we're dealing with triangles. Law of sines, law of cosines, they're going to deal with triangles. And so that means that when I hit the sine button and I check to see what mode I'm in, I don't want to be in radians like I was in the last unit. I want to be in degrees. So first thing, I'm going to hit the mode button, make sure I'm in degrees. And then I can go ahead and type this in. All right, so 5.3 sine 64 divided by sine of 82. And 4.8, in the instructions, it asked that we would round each answer to the nearest tenth if necessary. And so I went ahead and did that. All right, now I'm going to go ahead and solve the other one. So I'm going to cross multiply 5.3 times sine of 34 equals B times sine of 82. And then I'll solve for B by dividing by sine of 82. And B is approximately, that was what I just did, 34 over sine of 82. 2.99, if I round it to one decimal place, it's going to round up to 3.0. So the triangle is solved. I found the sides that were missing, and I found the one angle that was missing. All right, let's try the next one. So here they said that alpha is 30 degrees. And in this one, I just copy pasted that triangle down here and gave it to you to label. So alpha is 30 degrees. Beta is 88 degrees. And side A is 13. So if we look at this, we can see we have an angle and then a side. And so you can see if you go in a row, you have angle, angle, then a side, angle, angle, side. So this is another situation similar to the first one, but not identical, just a little bit different. But I'm going to start off the same. I'm still going to look for that third angle first, because finding the third angle of a triangle is the easiest math that I can do as a first step. So that missing angle is 62 degrees. And that is the Greek letter gamma, or the Greek letter that's kind of like a C. And it's not approximately, it's exactly equal to 62. There we go. Okay, and now I'm going to look for the information that I have in a pair. So I have a pair right here. I have 30 degrees and a side of 13. So I'm going to say sine 30 and 13, and then I'm going to look for what I want to solve. I've got sine 62 and then the side C that I need to solve for. So sine 62 over C, and then I'm going to set this up again. Sine 88 over B. All right, so I can cross multiply. 13 sine 62 equals C times sine 30. And then I'll go ahead and divide by sine 30. And I get 22.95, so that's 23.0. Okay, and then I'll solve this next one, cross multiply. 13 times sine of 88 degrees equals B times sine of 30 degrees. And we'll solve for B. I'm just going to copy paste this. 13 sine 88 over sine 30, 25.98, so that'd be 26.0. All right, so those cases, as you can see, the work is redundant, it's very similar. Those are going to be pretty easy for us to do. Now, the ambiguous case, the one that's a pain, they give us the information angle side side, and the reason that this is a pain is because it's vague. That's what ambiguous means. It means that it's vague. If you are given an acute angle alpha and the sides A and B, there's several possibilities, so it's vague. There's several possibilities for a triangle that can be drawn that have that same information. So one scenario, if you have an A that is less than the height, is that there could be no possible triangle drawn. If you have an A that is exactly the height of the triangle, you could draw one triangle. If you have A that is less than B, but greater than the height of the triangle, then there's actually two possible distinct triangles that could be drawn. And this is the case this is kind of what students don't like. This is what we're really gonna be watching out for, is a situation where you're given an angle and two sides and you have two possible triangles. And then if A is greater than B, then again, you have one possible triangle that can be drawn, and that's kind of similar to this situation where A equals the height of the triangle. So you don't have to memorize these, but what you do have to memorize is how you can start a problem like this and recognize, is it going to be a situation where I have two triangles? Is it going to be a situation where I have just one triangle? Or is it going to be a situation where no triangle is even possible? That is the part that is vague, and that's the part that makes this a pain. We have to know if we have 0 triangles, 1 triangle, or 2. And so that's what we're going to talk about next, is the ambiguous case and how do you know. So if you are given angle side side in a problem and you need to solve the triangle, always assume that there are 2 triangles. That's kind of the worst case scenario. So if we just assume that it's the worst case scenario, then we'll either be pleasantly surprised or we'll solve the problem correctly. So if I look at this information, it says that beta is 56.3 and side A is 8.3 and side B is 7.6. And if I look at this information, I can see that what they gave me is an angle and then a side and then another side. So I have angle, side, side. And as soon as I see that, I should draw a second triangle and label it exactly the same. So 56.3 degrees for angle beta, 8.3 for side A, 7.6 for side B. I should immediately just consider that there could be two triangles. I should assume that there's going to be two triangles. Okay, and then I'll go ahead and I'll get started with the solving. So here I only have one angle, so I can't start off by finding the third angle like I did with the other example problems. So the first thing I'm going to do instead is I'm going to look for a pair. I see a pair right here, the angle and the side across from it. So I'm going to start there. Sine of 56.3 divided by 7.6. And then I'm going to think about the other pair that I could make. The other pair that I could make is with this side and the angle across from it. So that is angle A, or angle alpha, and side A, which is 8.3. So I'm going to say sine of angle alpha divided by 8.3. And then I'm just going to go through and I'm going to solve that. So I'll cross multiply 8.3 times sine of 56.3 equals 7.6 times sine of alpha, and then I'll divide by 7.6. So 8.3 times sine of 56.3 divided by 7.6, and I get some decimal equals sine. And that makes sense because sine is, if we think about the graph of sine, it bounces back and forth between +1 and -1. So a decimal here is good. Makes a lot of sense. So I'm going to say sine alpha is approximately 0.9. And then to solve for the angle alpha, I just need to do sine inverse. So alpha is approximately, I'm going to do sine inverse of this decimal. So alpha is approximately 65.3 degrees. 65.3 degrees. So I'm going to label that. Okay, now I need to save this. This is important because this is going to determine everything else. It's going to determine if I have two triangles or if I have one triangle, and I already started solving it, so I know that 0 triangles is not the possibility here. So this is important. And in last unit, when we were doing chapter 6, we called whatever answer we got when we did sine inverse of something or cos inverse of something or tan inverse, we called that S. And so I'm going to call it S just to be consistent with that. So I'm going to hit store. I'm going to store this, and I'm going to use the letter S, which is right here, right above the ln key. So alpha ln, I'm going to store that as S, just to be consistent. And then on my paper, this is a Miss King thing. This is not like a mathematician thing. I just write an S with a little circle, and that tells me I stored it in my calculator so I remember. Okay, so, and the reason that I'm storing this, and this is important for this whole unit, the reason I'm storing this is that 65.3 is a good answer to write on my paper when the instructions told me to round to the nearest tenth. But I'm about to do more calculations, and if I use a rounded number, if I use 65.3 for the rest of my calculations, then every calculation after this is going to be wrong. I need to have my calculations based on this entire decimal, so I need all of this for the rest of my calculations for them to be accurate. All right, so what I'm going to do now is I'm going to start to work on my second triangle, but I'm not going to do very much. So I'm going to go up here, and I'm going to say that to find alpha in the second triangle, I have to remember chapter 6, what we learned in chapter 6. And in chapter 6, if we had one answer for sine, the second answer always came from doing pi minus the s value. But in this case, we're talking about triangles, and so instead of doing radians, pi minus the s value for the second answer, I'm going to do 180 degrees minus the s value. That's how I'm going to find the alpha in the second triangle. Okay, so I'll get there eventually, but I just want to finish the work on the first triangle first. But this is how we go from one triangle to another, is by doing this. And the reason we had to do that is because we took a sine inverse. We didn't do that in the first two examples. We did do it in this one. So that's what makes this one a little different. Okay, so I'm going to continue on in this triangle. Now I have two angles and I need to find the third angle. So for the third angle, I'm just going to do 180 degrees minus 56.3 minus 65.3. And I'm going to use the S when I do this one because I want my last angle to be accurate for when I do my future computations. So 180 minus 56.3 minus angle S. The rounded decimal 58.4 is fine for my answer. So 58.4, that's a good answer for what gamma equals. Gamma is 58.4 degrees, and that rounded decimal is totally fine, but we're going to need this entire decimal, not rounded, for us to be able to solve for side C. So what I'm going to do next is I'm going to go back to the original information I had in the beginning of the problem. I started with this pair of sine 56.3 divided by 7.6, so I'm going to go back there again. Sine 56.3 over 7.6. And now I'm going to use that last angle that I found, 58.4, and I'm going to use it to solve for this remaining side. So sine of 58.4 divided by C. And I'll go ahead and cross multiply. So 7.6 times sine of 58.4 equals C times sine of 56.3, and then I'll divide by sine of 56.3. So 7.6 sine of 58.4, I'm going to go up here and copy paste the 58.4. So I'm not using a rounded decimal, I'm using that whole decimal. Divided by sine of 56.3. This is a good decimal, it's not rounded, it was given to me in the original problem. And so I got this answer, 7.8, without rounding anything. So I have solved the first triangle. Found the two missing angles and the one missing side in that first triangle. All right, so now I'm going to move on to the second triangle. In the second triangle for alpha, I was going to do 180 minus S, and this is why we stored S, because at this point we've done a bunch of calculations and I want to be able to go back and get that S value again. So I'm going to do 180 minus S. And so my new alpha for this triangle is 114.7 degrees. 114.7 degrees. And what I'm going to do with this is I'm just going to make sure that if I look at these two angles, that this is still a valid triangle. That's what I want to make sure of. If this is 114 and this is 56, do I still have room for a third angle? And if I do, then I keep going. So if I look at this, I'm going to do 180 minus 56.3 minus the angle we just found that we're calling alpha. I still have a little bit of room left. I have a 9-degree angle there. So gamma is 9.0 degrees. I'm going to show my work off to the side. I want to make sure I always show my work on my example problems. There we go. Okay, so gamma is a 9.0 degree angle. And so we know for sure we have two triangles. We're actively solving for them now. Okay, so now I'm going to go back to that first pair that I had, the sine 56.3 over 7.6, and I can use that to find my last piece of missing information, which is the side across from gamma in this triangle. So I'm going to say sine 56.3 divided by 7.6 equals sine of gamma across from side C. And then I can go ahead and cross multiply. 7.6 sine 9 equals C times sine 56.3. And to solve for C, I'm going to divide by sine 56.3. And I get that C is approximately 7.6 times sine of that gamma degree measure, which was the 9 degrees. So I'm going to go up here, I'm going to copy paste this. So I'm not using a rounded decimal, I'm using the entire decimal. And then divide by sine of 56.3. Remember, this is not rounded, this is from the original problem. So 1.4. C is approximately 1.4 in this triangle. So because I was doing these problems and did not round until I was writing that decimal down as a final answer, this means that I can write my answer to the nearest tenth. I can write it to 1 decimal place and my answers will be right. Or if somebody asked me to write these answers to 5 decimal places, I could have written them to 5 decimal places as I was going and they would still be right, which is not always the case. If you round throughout the problem and use rounded decimals, then a lot of your decimals get pretty far off, especially if you're doing more than 1 decimal place of accuracy. So that's something to keep in mind. The book for these example problems was rounding to 1 decimal place. I'm not sure what my math lab is going to ask for these assignments, so just something to keep in mind. But I want you guys to be clear on we do not round when we are at this level of math. We do not round until the final answer. Anytime you're using a decimal in the middle of the problem, you should be storing the number or copy pasting the number. You should not be rounding until you're at the very end. Okay, let's try another example because I know that felt confusing probably. So this one says that we have gamma is 125 degrees. So I'm going to label that. Gamma is 125 degrees. Side B is 5.7. Side C is 8.6. So if I look at the information they gave me, here's an angle and a side and another side, so that's angle, side, side. And as soon as I see that, I start drawing a second triangle and I just assume that there's going to be 2 of them. Okay, so here there's only 1 angle that they gave us, there's not 2, and since there's 1 angle that they gave us, we can't start by solving for the missing angles. So what I'm going to do first, instead of just subtracting my angles from 180 degrees, what I'm going to do first is I'm going to start with the law of sines. I'm going to look at my pair. So I can see angle is 125, the side that goes with it is 8.6, and so I'm going to start by writing that down, sine of 125 over 8.6. And then I'm going to write down the next ratio that's going to help me solve for something that I don't know in the problem. So 5.7 is across from angle beta, and so that's what I'm going to look for next in the problem. Sine beta over 5.7. And now I can go ahead and solve by cross multiplying. So I've got 5.7 times sine of 125 equals 8.6 times sine beta, and I'll divide by 8.6. And so this decimal equals sine beta. So sine beta is approximately 0.5. And then from here, I can solve for beta. So sine inverse of this decimal is about 32.9 degrees. So beta is approximately 32.9 degrees. So 32.9 degrees. And this is the part where I say I used a sine inverse. Whenever you do a sine inverse, you can always get two answers. So I'm going to store this answer as my S value. Sine inverse is where we got the S value from the last chapter. So I'm going to go down here and I'm going to hit store and then alpha S. Okay, I'm storing that as S. And then whenever we were doing sine inverse, we always used pi minus S to get our second answer. And so for this unit, we're going to do 180 degrees minus S to get our second answer. Okay, so I'm going to stop there. I'm going to finish my first triangle before I go over to my second. I have two angles in here. I can go ahead and get my third angle. And I'm going to do that. I'll do my work up here. 180 degrees minus 32.9 minus 125. So minus this S value minus 125, 22.1 degrees. So angle alpha is 22.1 degrees. Okay, and now the very last piece of information I am trying to solve for is side A, which is across from angle alpha. So I'm going to say sine, I'm going to go back to the pair of information that I had when I very first started. So originally I had 125 and 8.6. So I'm going to say sine of 125 over 8.6. And now I'm going to solve for my missing piece of information. Sine of 22.1 over A. And I can cross multiply. So 8.6 times sine of 22.1 equals A times sine of 125. And I can divide by sine of 125. Okay, so 8.6 times sine of 22.1, and that's this decimal right here, so I'm going to go up and copy paste it, divided by sine of 125, and I get 3.95, which rounds to 4.0. So A is approximately 4.0. Okay, so in my first triangle, I found the two missing angles, I found the one missing side, so my first triangle is done. Now I'm going to look at my second triangle, and in my second triangle, I know that angle beta, which I stored in my calculator as S, let me go ahead and write that, I stored this as S in my calculator. Angle beta is where I start with on the second triangle. So in the second triangle, angle beta is going to be 180 degrees minus S. And so angle beta is 147.1 degrees. So beta is 147.1 degrees. And when I look at this, if I already had a 125 degree angle, and now I include a 147 degree angle, I have information here that cannot possibly be a triangle. 147 and 125 is more than 180 degrees. This is already more than a complete triangle, which means that this is not possible, and the information we were given only worked for a single triangle. So we drew two triangles, but there was only one, so we can stop there. Okay, so the difference between the two problems is that up here, when we did 180 minus S, we ended up with 114 degrees. And when we looked at 114 and the angle that they gave us, we still had room for a third angle that could add up to 180 degrees. This time when we did 180 degrees minus S, when we put it in there, it was already too big. It added to something greater than 180, and there wouldn't have been room for a third angle. And in that case, this can't be a second triangle. Okay, you know we're not done yet because we got to do the last situation. So here, we're going to draw this information again. We have angle alpha is 41 degrees. Side A is 3.3. Side B is 5.4. And when I look at this information, I can see that I've got an angle, and then I've got a side, and then I've got a side, and that makes angle side side. So as soon as I see that, I'm going to draw a second triangle. 41 degrees, 5.4, 3.3, right? I only have one angle, so I can't start off by subtracting something from 180 to find a missing angle. So what I'm going to have to do is start with the law of sines, and I'm going to look at my pair first. I have an angle, and I have a side that it goes with. And so I'm going to write sine of 41 over 3.3 equals, and then I'm going to look at what I'm trying to solve for first. I've got a side of 5.4 and the angle that it's across from, and so that's what I'm going to look at first. So sine of beta over 5.4. And I can go ahead and cross multiply. So 5.4 sine 41 equals 3.3 sine beta, and I'll divide by 3.3. 5.4 sine 41 over 3.3. And we get a decimal, but immediately there's actually a problem here. Sine B is approximately 1.1. This decimal is not between -1 and +1, it's greater than +1. And we know that a sine curve is supposed to be between -1 and +1. So what's about to happen is that when we try to solve this for beta, when we do sine inverse and try to solve this, we're going to get an error message on the calculator. So if I do sine inverse and go up here and grab the decimal and say sine inverse of that decimal, it won't work because you can't do sine inverse of a value that is less than -1 or greater than +1. So here there is no triangle that can be drawn with the given information. So no first triangle, no second triangle, no triangle period. Right? So those are the three situations you can have if the information that you're given is angle side side. And the key is that as soon as you see that the information you have is angle side side, you immediately draw two triangles. And when you're solving for the first angle and you have done sine inverse to solve, sine, I didn't write it down, but we had sine alpha equals 0.9. We did sine inverse to solve for alpha. What you do is in your second triangle, you go over here and you say, all right, for sine inverse, I also have to find a second answer. And my second answer is 180 degrees minus S. And that's where you're going to start the second triangle. So that is the key to doing this ambiguous case for law of sines. Okay? If you have angle, angle, side, or angle, side, angle, those are the easy ones, and you'll just enjoy using law of sines for those because it's a nice formula to work with. Okay, we're going to do an application problem next. So here it says we have the angle of elevation of the top of a water tower from point A on the ground is 19.9 degrees. So here's the angle of elevation and point A to the water tower. From point B, which is 50 feet closer to the tower, the angle of elevation is 21.8 degrees. What is the height of the tower? So this is what we're trying to solve for, the height of the tower. And this was a problem that could have been solved. There was a SOHCAHTOA section, end of chapter 5, I believe, and we skipped this problem. We didn't do it, I'm pretty sure. But now we're revisiting the problem and we're going to use law of sines to be able to solve it. So what I'm going to do is we still have a right triangle here, right? This one's a right triangle, and the right triangle is going to be beneficial because the side right here in the right triangle is part of what we're solving for. So I know at some point in this problem, I am going to use SOHCAHTOA, but before that, it would be really helpful if I could know what the length of this hypotenuse is. And so because I need that information, I'm going to look at this oblique triangle over here, this triangle that does not have a right angle, and I'm going to try to find as much missing information about that triangle as I can so that I can find this hypotenuse, okay? So this kind of stretched out triangle has 119.9 degrees right here. It has this kind of big angle right here. And this angle and the 21.8 degree angle, these two together make a straight line. So I know that a straight line is 180 degrees. So I'm going to do 180 degrees minus 21.8. Okay, so that big angle is 158.2. Okay. And then since I know these two angles, I can go up here and I can find this little angle up here. So 180 minus 19.9 minus 158.2, that's a 1.9 degree angle. That is tiny. Okay, 1.9 degrees. Okay, so I'm going to kind of draw this out, but I'm not going to draw it as extreme. So I'm going to say, so we have this is 19.9, this is 1.9, and this is 158.2. And I'm going to say this right here, between the 158.2 degree angle and the 1.9 degree angle, this side right here is the hypotenuse of the right triangle. I'm going to label it as H, and it would be really helpful for me to know what that H is, just because it could help me find the Y in this right triangle. And the reason that I chose to find the H, the reason I chose to find the hypotenuse is because it was the one side length that was the same between both triangles. It's part of the skinny triangle over here, but it's also part of the right triangle. So that's the only reason I'm trying to solve for it. Okay, this length down here is 50. Okay, so all I need to do is I need to look for two pairs of information so that I can use law of sines. I want an angle across from a side and another angle across from a side. And I'm going to try, if I can, to avoid the angle side-side situation, because I don't know if there's secretly a second triangle that has the same information and then maybe I get the wrong answer or something. So I'm going to try to be deliberate about the information I choose to use. So I know that I want to solve for H, so that means that I'm going to have to use this angle right here. I have to use that angle, okay? And then I have this side of 50, and so if I'm going to use law of sines and I'm going to have a pair of information, then I want to use the 1.9. I want this to be a pair. I'm just going to highlight these and see how I'm doing. So if I look at this information, that would be angle, angle, side, which is not the ambiguous case, and it works for law of sines. Angle, angle, side is perfect. So I'm going to go ahead and use this information. I'm going to start off with my pair. I've got sine of 1.9 over 50 equals sine of 19.9 over the hypotenuse that I'm going to solve for. And now I can go ahead and use the law of sines. So I'm going to cross multiply. I have 50 times sine of 19.9 equals H times sine of 1.9. And to solve for H, I can divide by sine of 1.9. So the hypotenuse is 513.3. What is this, feet? Okay, and now I need to solve for y. The only angle I have in this right triangle is the 21.8 degree angle. So that means that this side over here is the opposite side. This side right here is the hypotenuse. So if I'm using my right triangle trig, SOHCAHTOA, this would be O over H. This would be sine. So sine of the angle equals opposite over hypotenuse. And then to solve for y, I can just take this number and multiply it to the left side. So 513.3, this decimal times sine of 21.8 is the height of the tower. So the tower is 190.6 y. So the tower is approximately 191 feet tall. That was a lot of work. Okay, there is just a little bit more for us to go over. So if we look at this, they want us to talk about bearing, measuring angles and bearing angles, because those are going to come up in some of the application problems that we have coming up later on in this chapter. So just to remind you, standard position is the way that the angle is measured when you start with the positive x-axis as your initial side, and then you measure counterclockwise to the terminal side. So this is how we measure when we talk about the unit circle. We start over here on the positive x-axis, and then we measure this way. Bearing is where you measure an angle and you start from the positive y-axis. You start from due north, and then you measure clockwise. This is compass measurements. This is how they would measure if you are flying an airplane, or if you are hiking, probably, or if you're in a boat. Okay, so those are how you measure angles if you're doing something that's not math related, basically. Okay, so what we want to do is we want to be able to see angles that are oriented in different places and be able to see what they are in standard position, which is kind of their math notation, and also what they are if we were to say that they were bearing, which is kind of like their compass notation. So first we have angle A right here, and I got rid of all the numbers that are on here, so I'm just going to tell you that angle A is 30 degrees up from the positive x-axis. So angle A, if we were to say what it is in standard position, if it's 30 degrees up from the positive x-axis, then we would say, well, in standard position, this is a 30-degree angle. So standard position, that's a 30-degree angle. That's what we would call this in mathematics. If we're talking about this same position, but we're doing bearing, or we're talking about it from a compass perspective, we would say that from due north, we have gone clockwise 60 degrees. This would be bearing 60 degrees for that same position. All right, for angle B, if you had 30 degrees from here to here, then if we were to talk about this angle from the standard position, let me write this down, angle B, standard position. For standard position, we would say, well, this is 90, This is 90. This is 90. That's 270 degrees, right? 90, 90, 90. That's 270. Plus another 30 degrees. We would say, well, that's 300 degrees in standard position. But in bearing, we start at due north. So from due north, from here all the way down would be 180 degrees, but we are 30 less than that. So from here down to right here where B is, we would call this bearing 150 degrees. Bearing 150 degrees is what that one is. Okay, and then last, if we look at this one, if I said that this right here was a 45-degree angle, and I wanted you to say what angle C was in standard position and for bearing, then for standard position, we would say, okay, we've got 90 and another 90 makes 180, and 180 plus 45 gives you 225. So this would be a 225-degree angle from standard position. If we talked about this angle from bearing, if we started from due north and did bearing, we would say 90 degrees. Another 90 makes 180, and then this would also be another 45 degrees. So in bearing, it would be 90, 90 plus 45. It would also be 225. This is the only angle that is the same in standard position as it is bearing. All right. Next, I want to write the angles for bearing for each of these cardinal directions because sometimes in story problems, they don't say what the bearing is. They just say that it was headed east. Something was headed west. Something was headed northeast. And then you have to think about what that would be. So if we were talking about north, that would be bearing 0 degrees. If we talk about northeast, that is bearing 45 degrees. If we talk about east, that is bearing 90 degrees. I'm not going to write bearing every time because that takes a while to write. If we talk about southeast, that is bearing 135 degrees. If we talk about south, that is bearing 180 degrees. If we talk about southwest, that is bearing 225 degrees. West is bearing 270 degrees. And northwest is bearing 315 degrees. All right, and now that we understand how bearing works, we have one last application example. So this says a Bush pilot left the Fairbanks Airport in a light plane and flew 100 miles toward Fort Yukon in still air on a course with a bearing of 18 degrees. So this is where they start from Fairbanks, and they're flying bearing 18 degrees. So from due north, just 18 degrees, and they go 100 miles to this point B. Then she flew due east, which would be bearing 90 degrees. So due east is going this way. For some time, they don't say how long, but for some distance, to drop supplies to a snowbound family. So that's where they are over here. And then from here, her course to return to Fairbanks had a bearing of 225 degrees. So there's the 225 degree angle, and now she's coming back to Fairbanks. What was her maximum distance to Fairbanks? So her maximum distance, if you think about all the places she flew, her maximum distance would be right here, this length. because this is not her max distance. When she's right here, that's not her furthest distance. So we can tell just visually by looking at this, but that this side of the triangle that was formed must be the maximum distance. So here is the max distance, and so this is what we're going to solve for. All right, so I know that I'm trying to solve for side B, so I know I'm going to have to use this 108-degree angle. And then we're in the context of law of sines, so of course I'm expecting to use law of sines, and that means that I'm going to have to use another pair of information. I need another angle, I need another side length to go along with this so I can set up my law of sines. So my only other side length is this one over here, and the angle that would correspond to it would be this one right here. So I'm going to draw these in. And we know that this is a good sign because we have angle, side, which is nice for law of sines. It's not the ambiguous case, and so that's going to be good for us. And I want you to notice that whenever I write down the information for law of sines, I am not highlighting the side that I'm solving for. I'm only going to highlight the information that I'm given that I can use as actual numbers in the problem from the very start of the problem. And that's what determines if I'm angle side or angle side angle or angle side side. Okay, that's what makes that determination. So if I can have this information, this will be a good law of sines problem. It will be nice and easy to solve. I don't have to worry about the ambiguous case. So if I look over here, if this is a 225-degree angle, then I just need to know what this little piece of the angle is right here. And so I know that this is 90, this is 90, and this is 45. That's how they made that 225-degree angle, which means that this angle that kind of finishes up this quadrant right here, this angle must be 45 degrees as well. And so now I have enough information that I can do my law of sines. So here's my pair, sine 45 and 100. Equals sine of 108 over the side that we're solving for. And to solve this, I'm going to go ahead and cross multiply. So 100 times sine of 108 equals b times sine of 45. And to solve for b, I'm going to divide by sine of 45. $134.5. B is approximately 134.5. And this was, what were the units? Miles. So the furthest away that she was, her maximum distance from Fairbanks was approximately 134.5 miles.